You land on Mars. Your first breath in the suit tastes of stale fear. The ground is cold, the silence absolute. Every step on this red desert writes a single word in your bones, irreversible. And then reality hits you like a meteor strike. You're never going home. And here is a question. If you could ask the first Mars colonist anything after they've been there for a year, what would it be? Let us know in the comments. I will pin the most creative answer. Now let's begin. The journey to Mars isn't just difficult, it's a test of human endurance that pushes our biology to its absolute breaking point. When we talk about sending humans to another world, we're not just talking about building a bigger rocket or packing enough snacks for the road trip. We're talking about fundamentally challenging what it means to be human in an environment that evolved without us, that has no interest in keeping us alive, and that will fight our survival at every turn. Let me share something that might surprise you. We've been studying Mars for decades. Our robotic scouts, from the Viking landers of the 1970s to the Perseverance rover rolling across Jezero crater right now, have sent back an enormous amount of data. They've told us about ancient riverbeds, discovered organic molecules, and even detected methane in the atmosphere that appears and disappears with the seasons. These discoveries are breathtaking. They suggest Mars once had conditions suitable for life. Maybe it still does, hidden in underground aquifers or protected pockets we haven't found yet. But here's what all that data also tells us. Mars is spectacularly hostile to human life. And I'm not talking about the kind of hostile where you need to pack a jacket. I'm talking about the kind of hostile where every single second of every single day, the planet is actively trying to kill you in ways both obvious and terrifyingly subtle. Let's start with something fundamental: gravity. On Earth, we experience one standard gravity, what scientists call 1G. Your bones, your muscles, your cardiovascular system, even the fluid balance in your cells, all of it evolved over millions of years to function under this specific gravitational pull. On Mars, gravity is only about 38% of Earth's. That might sound pleasant at first. You'd weigh much less. You could jump higher. But your body doesn't interpret low gravity as a fun feature. Your body interprets it as a catastrophic emergency. During the Artemis 1 mission in 2022, instruments aboard the Orion spacecraft measured radiation exposure during a lunar trajectory. The data was eye-opening. Even on that relatively short journey, just 25 days, the spacecraft and its future human passengers would be exposed to radiation levels significantly higher than anything experienced on Earth or even in low Earth orbit aboard the International Space Station. Now multiply that exposure time by 10 or more for a Mars mission, and you begin to see the scope of the problem. Here's something most people don't realize. Space itself is filled with two types of deadly radiation. The first type comes from our own sun. Solar particle events, or SPEs, happen when our star burps out massive amounts of charged particles during solar flares or coronal mass ejections. These events are unpredictable and can be catastrophic. The second type, galactic cosmic rays, or GCRs, are even more insidious. These are high-energy particles that have been accelerated by distant supernovae, stellar explosions so powerful they echo across the galaxy. GCRs are traveling at nearly the speed of light, and when they slam into human tissue, they don't just damage cells, they shred DNA, create cascades of secondary radiation, and leave a trail of biological destruction in their wake. On Earth, we're protected. Our planet's magnetic field acts like an invisible shield, deflecting most of this radiation away. The atmosphere provides another thick blanket of protection. Even on the International Space Station, astronauts still benefit from some of this shielding because they're orbiting within Earth's magnetosphere. But on the journey to Mars, there's nothing between you and the cosmos. You're naked in the universe, and the universe doesn't care. If you're enjoying this deep dive into space exploration, make sure you hit that subscribe button and give this video a thumbs up. It really helps the channel grow, and it tells me you want more content like this. Recent research published in 2026 in the European Physical Journal examined the combined effects of radiation and microgravity on human physiology. What they found is deeply concerning. These two hazards don't just add together, they multiply each other's damage. Radiation exposure alters how your cells function, making them more vulnerable to the stress of weightlessness. Meanwhile, microgravity changes how your body repairs radiation damage, making you more susceptible to cancer, cardiovascular disease, and central nervous system impairment. Your body becomes trapped in a vicious cycle where each problem makes the other worse. Let me paint you a picture of what happens to a human body during the 7-month journey to Mars. First, your bones begin to dissolve. Without the constant stress of gravity pulling you down, your skeletal system decides it doesn't need to maintain its density. You lose about 1 to 2% of your bone mass every month. That's the equivalent of what an elderly person with osteoporosis might lose in an entire year, except you're experiencing it in weeks. Your hips, your spine, your legs, they're all quietly crumbling inside you. Your muscles follow the same path. Despite exercising 2 hours every single day, something astronauts on the ISS must do religiously, you'll still lose significant muscle mass and strength. Your heart is a muscle too, and in microgravity, it doesn't have to work as hard to pump blood, so it shrinks. It becomes weaker. This is catastrophic because when you finally reach Mars and experience even that reduced gravity, your weakened heart has to suddenly start working harder again. Your vision changes. Fluid shifts in your body cause intracranial pressure to build up, literally squeezing your eyeballs from behind. Some astronauts have returned from space with permanent vision damage, a condition called spaceflight-associated neuroocular syndrome. Your immune system becomes compromised. Your body starts reactivating dormant viruses like chickenpox that have been hiding in your nerve cells for decades. You become more susceptible to infections at exactly the moment when getting sick could be fatal. And through all of this, you're being irradiated every day, every hour, every second. The radiation is damaging your DNA, increasing your lifetime cancer risk with each passing moment. Some estimates suggest that a round trip to Mars could expose astronauts to radiation doses that would violate every safety standard we've ever established for workers on Earth. We're talking about increasing your lifetime cancer risk by several percentage points. That might not sound like much, but when you're starting from a baseline, adding 3 to 5% to your chances of developing fatal cancer is absolutely significant. But let's say you make it. You survive the journey, your bones are weaker, your muscles have atrophied, your heart is smaller, your vision might be permanently damaged, and you've absorbed a lifetime's worth of radiation, but you made it. You're approaching Mars. The red planet fills your window, and despite everything, you feel a surge of hope. You're about to become one of the first humans to set foot on another world. Surely the hard part is over, right? Surely, once you land, things will get easier. That's when the real nightmare begins. Mars doesn't want you there. Let me be completely clear about this. The planet isn't neutral. It isn't indifferent. Every aspect of its environment is fundamentally incompatible with human survival. And the moment you step out of your landing craft onto that rust-colored soil, you're entering a world that will challenge every biological system you possess. Let's talk about the atmosphere, or rather, the lack of one. Earth's atmosphere at sea level exerts a pressure of about 14.7 pounds per square inch. This pressure is so constant, so normal to us, that we don't even think about it. But it's essential. It keeps our bodily fluids liquid. It allows our lungs to extract oxygen. It maintains the delicate balance of gases dissolved in our blood. Mars has an atmosphere technically, but calling it an atmosphere is generous. The atmospheric pressure on Mars is less than 1% of Earth's. That's not an exaggeration. It's 0.006 times Earth's pressure. To put that in perspective, that's equivalent to being at an altitude of about 100,000 feet above Earth. The highest altitude any human has reached in a balloon was around 128,000 feet, and that person was wearing a full pressure suit because at that height, your blood literally boils. Not from heat, but from the lack of pressure. Water in your tissues begins to vaporize. This is called ebulism, and it's exactly as horrible as it sounds. So on Mars, you cannot take off your spacesuit, ever. Not for a second, not to scratch your nose, not to wipe sweat from your eyes, not even in an emergency. The moment your skin is exposed to the Martian atmosphere, you have about 15 seconds before you lose consciousness. Your lungs would attempt to exhale against a vacuum. The moisture on your tongue, in your mouth, on your eyes would begin to boil. You wouldn't explode like in the movies, but you'd swell up like a balloon as the gases in your body expanded. It would be agonizing and it would be fatal. And that's before we even discuss what you'd be breathing. The Martian atmosphere is 95% carbon dioxide. There's almost no oxygen, just 0.13% compared to Earth's 21%. Even if the pressure were somehow normal, you'd suffocate immediately. You can't breathe carbon dioxide. Your body produces it as waste. Trying to breathe the Martian atmosphere would be like trying to survive by breathing your own exhaust. The temperature is another delightful challenge. Mars is cold, not winter in Canada cold, not Antarctic research station cold. We're talking about average temperatures around -80 degrees Fahrenheit or -62 Celsius. At the equator, on a nice summer day, temperatures might climb up to a balmy 70 degrees Fahrenheit. But at night, in that same spot, it could plummet to -100 degrees. Your habitat needs to protect you from temperature swings of more than 150 degrees within a single day-night cycle. Speaking of habitats, let me tell you about one of the most underestimated dangers on Mars: dust. Martian dust isn't like the dust on Earth. It's incredibly fine, about the consistency of talcum powder, and it gets everywhere. I mean everywhere. It clings to everything because it's electrostatically charged from the constant friction in the thin atmosphere. The Apollo astronauts who walked on the Moon, which has similar dust, reported that it was one of their biggest challenges. The lunar dust abraded their spacesuits, clogged mechanisms, and was nearly impossible to keep out of their living quarters. But Martian dust is potentially worse because it contains perchlorates. These are chlorine compounds that are toxic to humans. They can interfere with thyroid function and, in high enough concentrations, can be lethal. Every time you enter your habitat from outside, you're potentially bringing in these toxic particles. You'd need elaborate airlock systems, constant cleaning protocols, and you'd still never fully eliminate the exposure. Over months and years, this chronic, low-level exposure to perchlorates could cause serious health problems. And then there are the dust storms. Mars is famous for its global dust storms, events so massive they can envelop the entire planet for weeks or months at a time. In 2018, a dust storm covered the entire surface of Mars and effectively ended the Opportunity rover's mission after almost 15 years of operation. The storm blocked out so much sunlight that the solar-powered rover couldn't recharge its batteries. If you're relying on solar power for your habitat and a global dust storm hits, you could be plunged into darkness and cold for months. Your backup systems better be really, really good. Now, I know what some of you might be thinking. We've talked about challenges before in space exploration. The Apollo missions faced enormous challenges. The International Space Station required solving countless problems. We're humans, we're clever, we innovate, we overcome, and you're absolutely right, we do. But here's the critical difference. Every previous space mission had an escape route. If something went catastrophically wrong on the ISS, astronauts could evacuate in a Soyuz capsule and be back on Earth within a few hours. The Apollo astronauts, even when they were 250,000 miles away on the Moon, were only a few days from home. Mars is different. Mars is hundreds of millions of miles away, and that distance changes everything. Actually, speaking of places in space that will challenge everything you think you know, I recently created a video about why the Moon is the scariest place in space. We often think of the Moon as familiar, almost friendly, since we've sent humans there before. But the lunar environment has some truly terrifying characteristics that most people never consider. If you're fascinated by the extreme dangers of space environments, you should definitely check out that video after this one. The link is in the description. But back to Mars, let's talk about launch windows and orbital mechanics. Earth and Mars are both orbiting the Sun, but at different speeds and distances. There's only a brief period, roughly every 26 months, when the two planets are positioned in a way that makes a trip between them feasible with current rocket technology. These are called launch windows, and they're absolutely critical for mission planning. If you launch during the optimal window, the journey to Mars takes about 6 to 7 months. If you miss that window, you could be looking at a journey that takes significantly longer and requires much more fuel. But here's the problem. If something goes wrong and you need to abort the mission and return to Earth, you can't just turn around. You have to wait for the next launch window when the planets are properly aligned again. That could be nearly 2 years away. Think about that for a moment. 2 years. If there's a medical emergency, if a critical system fails, if someone has a psychological breakdown, if there's an accident that damages your life support, you cannot leave. You cannot call for help that will arrive in time. You are on your own, separated from Earth by a gulf of space and time that no rescue mission could possibly cross quickly enough to save you. This is fundamentally different from any exploration humanity has ever attempted. When early sailors explored the Pacific Ocean, the journeys were dangerous and long, but they could always try to turn back. When explorers trekked across Antarctica, they could attempt to return to their bases if conditions became unbearable. Even on the ISS, help is just a launch away. But on Mars, you are committed. You are isolated in a way that no human has ever been isolated before. The psychological impact of this isolation cannot be overstated. Research conducted on Earth-based analogues, places where scientists simulate Mars missions in isolated environments, has shown that even highly trained, psychologically screened individuals begin to experience significant stress, interpersonal conflicts, and mental health challenges after just a few months of isolation. Now imagine extending that isolation, not for months, but for years. Imagine knowing that everyone you've ever loved, every familiar place, every comfort of home, is on a world you can see in the sky but can never reach. The communications delay alone is enough to drive you mad. Radio signals travel at the speed of light, which sounds fast, and it is. But Mars is so far away that even light takes between 3 and 22 minutes to make the trip, depending on where the planets are in their orbits. This means that when you talk to mission control, when you talk to your family, there's a delay of anywhere from 6 to 44 minutes between when you ask a question and when you can possibly receive an answer. You can't have a conversation. You can't call for help and get immediate advice. If something is going wrong, if you're facing an emergency that requires expert input to solve, you're going to be recording messages, sending them to Earth, and then waiting an agonizing 20 to 40 minutes to hear back. By then, you might already be dead. Every decision has to be made by you and your crew in real time, with no safety net, no expert advice available when you need it most. This creates a level of autonomy that sounds empowering, but is actually terrifying. You and your small crew are responsible for absolutely everything. There are no specialists you can call. There's no one coming to fix things if they break. You are the entire support network, the entire knowledge base, the entire emergency response team for a mission taking place on an alien world. And your body continues to deteriorate. Remember how I mentioned that your bones and muscles waste away during the journey to Mars? Well, landing on the red planet doesn't fix that problem. fact, it might make things worse in ways we're only beginning to understand. Mars has gravity, yes, but it's only 38% of what you're used to. Your body, which has already spent 7 months in zero gravity and has lost significant bone density and muscle mass, now has to adapt to yet another gravitational environment. But here's the cruel irony, that 38% gravity isn't enough to stop the deterioration. It's enough to make you work harder than you did in 0G, which sounds good until you realize your weakened body now has to perform all the physical labor of setting up habitats, conducting experiments, and maintaining equipment while operating at a fraction of its normal capacity. Recent studies published in 2025 and 2026 have revealed something deeply troubling. Scientists created digital twin models to monitor the relationship between astronaut movements and muscle activity. What they discovered is that even with rigorous exercise protocols, astronauts arriving at Mars might not be able to walk effectively. Let me repeat that. After 7 months in space, you might land on Mars and discover that your legs, despite months of exercise, simply cannot support you reliably even in the reduced gravity. Imagine that scenario. You've traveled farther than any human in history. You're standing on the surface of another planet, and you can't walk without assistance. You're trapped in a body that has betrayed you, weakened by forces you can't control, on a world that offers no mercy for weakness. Every task takes longer, every movement requires more effort. And your body isn't recovering, it's continuing to adapt to this new, low-gravity environment in ways that make returning to Earth's gravity increasingly difficult. This is where we need to talk about something that mission planners don't like to discuss publicly: the point of no return. Not the point in the journey where you can't turn back, but the point in your physical adaptation, where your body has changed so fundamentally that returning to Earth becomes medically inadvisable or even impossible. Scientists call this the space exposome-intergrome interaction, which is a fancy way of saying that your body's exposure to the space environment creates changes in how all your biological systems interact with each other. These changes accumulate over time. Some of them might be reversible if you return to Earth quickly enough, but others, particularly changes to your cardiovascular system, your bone structure, your vision, and potentially even your brain function, may become permanent. There's research suggesting that after a certain amount of time in reduced gravity, your heart literally remodels itself. It becomes smaller, weaker, adapted to pumping blood in a low-gravity environment. If you then tried to return to Earth's full gravity, your heart might not be able to handle the increased workload. You could experience heart failure. The very act of coming home could kill you. Your bones present a similar problem. The bone loss you experience in space is severe, but it's the recovery that's truly concerning. When astronauts return from 6-month stays on the ISS, it can take years for their bones to recover, and in many cases they never fully regain the bone density they had before launch. Now imagine spending not 6 months but 2 to 3 years in low or reduced gravity. The bone loss would be catastrophic. Even if you could survive the return journey, you might spend the rest of your life on Earth at extreme risk for fractures, unable to walk without assistance, your skeleton permanently compromised. Then there's radiation exposure, which we've talked about, but let me emphasize this point. Radiation damage is cumulative and permanent. Every day you spend in space, every day you spend on Mars with its thin atmosphere and no magnetic field, you're accumulating radiation damage to your DNA. This increases your cancer risk, damages your cardiovascular system, and may even cause cognitive decline. The more time you spend away from Earth's protective embrace, the more damage you accumulate, and the less likely you are to live a long, healthy life, even if you do make it home. So here's the nightmarish calculation that the first Mars astronauts will have to make. At what point does staying on Mars become safer than trying to return to Earth? At what point has your body adapted so completely to the Martian environment that Earth itself becomes the hostile alien world you can no longer survive on? This brings us to one of the most profound reasons why the first humans on Mars might never return: economics and logistics. Let me break down exactly what a Mars mission actually requires, and you'll start to see why bringing people back might simply be impossible. First, you need to get to Mars. This requires an enormous rocket, likely something like SpaceX's Starship or NASA's Space Launch System. These are the largest, most powerful rockets ever built, and they're barely capable of sending the necessary payload to Mars. The spacecraft that makes the journey needs to carry not just humans, but all the life support, food, water, equipment, and supplies needed for a 7-month journey through deep space. Then you need a landing system capable of safely delivering humans and cargo to the Martian surface. This is incredibly difficult because Mars' thin atmosphere provides very little to work with for aerobraking, but it's thick enough to require heat shields. You're trying to slow down from thousands of miles per hour to a safe landing speed using an atmosphere that's less than 1% as thick as Earth's. Once on the surface, you need habitats that can protect humans from radiation, temperature extremes, dust storms, and the toxic environment. You need power generation systems, probably nuclear since solar panels would be less effective and vulnerable to dust storms. You need water extraction and purification systems. You need oxygen generation, carbon dioxide scrubbing, temperature control, waste recycling, medical facilities, repair equipment, spare parts, and so much more. And here's the kicker: you need all of this equipment to work perfectly without major failures for years. There's no running to the hardware store for a replacement part. There's no calling a technician. If something breaks and you can't fix it with what you have on hand, people die. But let's say everything works. Your habitats are functioning, your life support is running, you're producing food, extracting water from Martian ice, and generating oxygen. You've established a base. Now, to bring you home, you need a rocket. Not just any rocket, but a rocket capable of launching from Mars' surface, which still has significant gravity and a thin atmosphere, and then making the 6 to 7 month journey back to Earth. This rocket needs fuel, a lot of fuel. And that fuel either needs to have been sent to Mars ahead of time, which means multiple additional missions and landing sites full of fuel storage, or it needs to be manufactured on Mars using local resources. This is called in situ resource utilization, or ISRU. And while it sounds great in theory, it requires building essentially a chemical processing plant on Mars that can extract carbon dioxide from the atmosphere, water from the soil, and combine them to create rocket fuel. This plant needs to work flawlessly. It needs power, maintenance, and time. Some estimates suggest it could take months or even years to generate enough fuel for a return trip. During all that time, your crew is living on Mars, their bodies deteriorating, radiation damage accumulating, waiting for their ticket home to be manufactured molecule by molecule. And then, even if you have the fuel, you need the return spacecraft to still be functional. It's been sitting on Mars for years, exposed to the harsh environment, the temperature extremes, the dust, the radiation. Components degrade, seals fail, electronics can be damaged. The spacecraft needs to be maintained and tested, but you can't exactly take it for a test drive. The first time you fire up those engines better be when you're launching for real, and they better work perfectly because you don't get a second chance. Let's talk numbers for a moment. The cost of sending a single kilogram of payload to Mars is estimated to be somewhere between $20,000 to hundreds of thousands of dollars, depending on the mission architecture and technology used. A human being with their spacesuit, their seat, their share of the life support systems, their food and water for the journey probably represents at least 100 kilograms of mass, but realistically, much more. Now multiply that by the fuel needed for the return journey, the spacecraft itself, all the supplies for the return trip, and you're looking at potentially hundreds of tons that need to be either sent from Earth or manufactured on Mars. The economic cost is staggering, potentially hundreds of billions of dollars for a single mission. Here's the brutal truth. It might be economically impossible to bring the first Mars crew home. Not because we don't want to, but because the resources required to mount a return mission might exceed what any government or organization is willing or able to spend. It's cheaper, more practical, and more logical to send additional supplies and personnel on one-way trips than to invest the astronomical sums required to bring the first crew back. This is why some Mars mission concepts have always been explicitly one-way. The Mars One project, before it collapsed, was planning to send people to Mars with no return trip planned. The idea was to establish a permanent settlement, with new crews arriving every few years to expand the base. The first settlers would live out their lives on Mars, becoming the first permanent human residents of another world. SpaceX's Elon Musk has spoken about Mars colonization as a multi-planetary insurance policy for humanity. The vision isn't to visit Mars and come back. It's to go to Mars and stay, to build cities, to have children born on Mars who've never known Earth's gravity and might never be able to visit the world their parents came from. There's something profoundly haunting about the idea of children born on Mars. Think about it for a moment. A human baby conceived and born in 38% gravity, developing in an environment completely unlike the one our species evolved in for millions of years. What would that do to a developing body? Would their bones grow properly? Would their hearts develop the strength needed to ever visit Earth? Would their immune systems function normally? We don't know. We have absolutely no data on this because it's never happened. Everything we understand about human development is based on one gravitational constant, Earth's gravity. Remove that constant, change it to something weaker, and we're conducting an experiment on human biology that has never been attempted. The first child born on Mars would be, in a very real sense, a new branch of humanity, a Martian human adapted from birth to a world that would kill their Earth-born parents without constant technological intervention. And here's the heartbreaking part. That child might never be able to come to Earth. If their cardiovascular system, their skeleton, their muscles all develop in low gravity, bringing them to a planet with more than twice the gravitational pull they've ever experienced could be fatal. They would be prisoners of Mars, not by choice, but by biology. Born on one world, forever unable to visit the ancestral home of their species. This raises questions that go far beyond engineering and physics. These are questions of ethics, of human rights, of what it means to consent to an existence. Can you ethically bring a child into the world knowing they'll be trapped on a hostile planet, dependent on technology for every breath, every drop of water, every moment of their existence? Yet this might be inevitable if humanity is serious about becoming a multi-planetary species. But let's step back from the distant future and return to the first crew. Let's talk about what their daily life would actually look like, because understanding the reality of living on Mars helps explain why leaving might become impossible, even if the technology existed. Your day on Mars starts in a habitat module that's probably not much bigger than a large RV. You're sharing this space with maybe 3 to 6 other people, and you'll be sharing it for years. Privacy is a luxury you left behind on Earth. You wake up to artificial lighting because your habitat has no windows. Windows are structural weak points, and on Mars, they're also radiation hazards. Every photon of sunlight that comes through a window brings radiation with it. You put on your clothing, probably the same outfit you've been wearing for days because water is too precious to waste on laundry. Everything is recycled on Mars. Your sweat is captured and purified. Your urine is processed back into drinking water. Even the moisture in your breath is collected and returned to the water supply. You're living in a closed-loop system where waste is a concept that can't exist. Everything must be reused, recycled, regenerated. Breakfast is probably a rehydrated meal or something grown in the habitat's greenhouse. And yes, growing food on Mars is possible, but it's incredibly challenging. You need to create artificial soil using Martian regolith that's been cleaned of perchlorates. You need water, which you're extracting from ice deposits and recycling endlessly. You need light, which requires energy. You need a controlled atmosphere with the right mix of gases, humidity, and temperature. The plants you grow aren't going to be diverse. You'll focus on high-calorie, nutrient-dense crops. Potatoes, like in the movie The Martian, actually make sense. Wheat, soybeans, leafy greens. But forget about variety. You're eating for survival, not pleasure. The psychological impact of eating the same limited menu for years cannot be underestimated. Food is one of life's great pleasures, and on Mars, it becomes a bland necessity. After breakfast, you suit up. This isn't like putting on a coat. A Mars spacesuit is a personal spacecraft. It has to provide pressure, oxygen, temperature control, carbon dioxide removal, and radiation protection. Getting into one takes time and requires help. You're checking seals, verifying systems, running diagnostics. A failure in your suit means death, so you check everything twice. Then you enter the airlock, depressurize, and step outside into a landscape that looks like it came from a nightmare. The sky isn't blue. It's a butterscotch tan during the day, fading to blue-gray at sunset because of how the thin atmosphere scatters light differently than Earth's. The ground is rusty red, covered in rocks and dust, stretching to a horizon that's noticeably closer than Earth's because Mars is a smaller planet. The Sun is smaller in the sky, about 2/3 the size it appears from Earth, because Mars is about 50% farther from the Sun than we are. The light is dimmer, giving everything a perpetual twilight quality even at noon. The temperature, which might be tolerable in the sunlight, plummets the moment you step into shadow. You have work to do. Maybe you're maintaining the solar panels, cleaning dust off their surfaces to maximize power generation. Maybe you're checking the water extraction equipment, making sure the heating elements that melt subsurface ice are functioning properly. Maybe you're conducting geological surveys, collecting samples, analyzing the composition of rocks and soil to better understand Mars' history and to search for any signs of past or present life. Every task takes longer than it would on Earth. Your suit is bulky and restricts movement. The gloves are thick, making fine motor control difficult. You can't just kneel down and pick something up. You have to plan every movement, conserve your energy, because you're already working with reduced cardiovascular capacity and weakened muscles, and you're constantly aware of the radiation. You can't see it, can't feel it, but it's there, sleeting through you every second. Your suit provides some protection, but not enough. Every hour you spend outside increases your cumulative dose. Mission planners track this obsessively because there are limits, thresholds beyond which the cancer risk becomes unacceptable. But on Mars, you might not have a choice. The work has to be done, and you're the only one who can do it. After several hours, you return to the airlock. You go through decontamination procedures to remove as much Martian dust as possible. You depressurize, remove your suit, and undergo medical checks. How's your heart rate? Your blood oxygen? Any signs of suit failure or exposure? Then you document everything. Every observation, every equipment reading, every anomaly gets recorded and transmitted back to Earth. The communication delay means you're not having conversations with mission control. You're sending detailed reports and receiving detailed instructions hours later. Sometimes you'll record video messages for family and friends, trying to maintain some connection to a home that feels increasingly abstract and distant. Evenings are perhaps the hardest time psychologically. The work is done. You're back in the cramped habitat with the same people you've been living with for months or years. You're eating another rehydrated meal. You're trying to find some form of entertainment or relaxation in an environment that offers neither privacy nor variety. Some crews might have small libraries of books, movies, and music loaded on computers. Some might exercise, though you've already spent hours on that today. Some might just talk, sharing stories, memories of Earth, dreams of what they'll do when they get home. Except, increasingly, that dream of home becomes a fantasy rather than a plan. Because here's what's happening while you're living this existence. Earth is moving on without you. Every day you're on Mars is a day where the people you love are aging, changing, living their lives. Your friends are pursuing careers, falling in love, having children, experiencing joys and sorrows that you'll only hear about in delayed messages. Your parents are getting older, and you're not there. If someone gets sick, if there's an emergency, if someone dies, you'll find out hours or days after it happens, and you can't do anything about it. The psychological term for this is ambiguous loss, a grief that comes from separation without closure. You're not dead, but you're not present either. You exist in a strange liminal space, neither here nor there, and the people on Earth have to process your absence while knowing you're alive somewhere impossibly far away. Over time, this separation becomes harder to bridge. When you do come home, if you come home, will you still fit into the life you left behind? Will your relationships have survived years of separation and delayed communication? Will you even recognize yourself after years of living in such an extreme environment? Studies of Antarctic research stations, submarines, and other isolated environments have shown that people change in isolation. They develop new personalities, new coping mechanisms, sometimes new psychological issues. And those are environments on Earth where rescue is theoretically possible and the isolation is temporary. On Mars, the isolation is profound and the duration is open-ended. There's also the question of purpose. The first Mars crew will be there as explorers, as scientists, as pioneers. They'll have clear missions and objectives. But what happens when those missions are complete? What happens after you've set up the base, conducted the initial surveys, established the life support systems? Do you just wait for the next crew to arrive? Do you wait for the fuel to be manufactured for a return trip that might never come? This existential uncertainty is perhaps the cruelest aspect of the Mars mission. You're living in a state of perpetual suspension where every plan is tentative and every promise is conditional. The return mission depends on funding that might be cut. It depends on technology that might fail. It depends on political will that might evaporate. You're told you'll come home, but deep down you know that you might not, and that knowledge colors every day you spend on that rusty red planet. Let me tell you about something that doesn't get discussed enough in the popular media coverage of Mars missions. The psychological phenomenon called Earth out of view. Astronauts on the International Space Station, and even those who traveled to the Moon, could still see Earth. That pale blue sphere hanging in the blackness served as a constant reminder of home, a visual anchor to everything familiar. It provided psychological comfort that's difficult to quantify but impossible to overstate. On Mars, Earth is just another point of light in the sky. You can see it, yes, but only as a bright star. You can't make out continents or clouds. You can't see the blue that makes our world unique in the solar system. Home becomes an abstraction, a memory, something you know exists but can no longer truly perceive. This disconnection from visual contact with Earth has been theorized to have profound psychological effects that we won't fully understand until someone actually experiences it. Astronaut accounts from the Moon missions often describe the overwhelming emotion of seeing Earth from that distance. The Apollo 8 crew, the first humans to orbit the Moon in December of 1968, spoke about how fragile and precious Earth looked from lunar orbit. That perspective, now called the overview effect, gave them a profound sense of connection to humanity and to our planet. But on Mars, you don't get that perspective. You get isolation. You get the constant, grinding awareness that you are farther from home than any human has ever been, living on a world that actively resists your presence. And then there's the terror that nobody talks about. Equipment failure. Every single system that keeps you alive is mechanical. Machines break, electronics fail, seals degrade, filters clog. And on Mars, when something breaks, you can't order a replacement part. You can't call a specialist. You have whatever spare parts and materials you brought with you, and you have your own ingenuity, that's it. Imagine your water recycling system develops a fault. Water is life. Without it, you have maybe a week before you die of dehydration. You need to diagnose the problem, figure out a repair using only the tools and materials available, and implement that repair successfully, all while managing the stress of knowing that failure means death. And you can't ask mission control for real-time help because of that communication delay. By the time you send them a description of the problem and receive their suggestions, hours have passed, hours you might not have. This constant low-level stress, this awareness that you're always one critical failure away from catastrophe, takes a tremendous psychological toll. Sleep becomes difficult, anxiety becomes chronic. Some crew members might develop what's essentially a form of post-traumatic stress disorder, except it's not post, because the trauma is ongoing and unrelenting. NASA and other space agencies conduct extensive psychological screening for astronauts. They look for people with exceptional stress tolerance, people who remain calm under pressure, people who work well in teams and can handle isolation. But there's a limit to what screening can predict. Nobody has lived on Mars. Nobody has experienced that specific combination of isolation, danger, physical deterioration, and existential uncertainty for years at a time. We're selecting the best people we can find and hoping they'll be resilient enough, but we won't really know until we try. And here's something chilling. What happens if someone has a complete psychological breakdown on Mars? On Earth, if someone becomes suicidal or psychotic, we have hospitals, medications, trained professionals. On Mars, you have a small crew who are all dealing with their own stress, limited medical supplies, and no ability to evacuate the person to a safe environment. A psychological crisis becomes an emergency that threatens the entire mission. If someone decides they can't take it anymore and tries to harm themselves or others, or if someone becomes so mentally compromised they can no longer function, the other crew members have to handle it. They might have to physically restrain a colleague, someone they've lived with for years, someone they consider family. They might have to make impossible decisions about sedation, isolation, or restraint. And they have to do all of this while continuing to maintain the habitat and keep everyone else alive. This is the dark reality that mission planners prepare for, but hope never happens. Psychological emergencies in space are potentially more dangerous than equipment failures because humans are unpredictable. A machine fails in ways you can diagnose and repair. A human mind in crisis is infinitely more complex and potentially more destructive. Now let's talk about something that might sound mundane but is actually critical: governance. Who's in charge on Mars? How are decisions made? What happens when crew members disagree about something important? On Earth, we have legal systems, social structures, hierarchies that have evolved over thousands of years. On Mars, you have a handful of people living in an artificial environment with no precedent for how to organize themselves. Initially, there will be a mission commander, someone designated by the space agency that sent the mission. But as time passes, especially if the crew becomes effectively permanent residents, does that commander retain authority? Do the crew members establish their own system of governance? What if someone refuses to follow orders? What if there's a mutiny? These aren't hypothetical questions. History is full of examples of isolated groups developing internal conflicts. Expeditions to Antarctica have experienced crew members refusing to work together. Submarine crews have had incidents of violence and insubordination, and those are situations where everyone knew they were going home eventually and where military discipline provided structure. On Mars, without clear end dates and with the possibility that the crew might be there permanently, the potential for social breakdown is significant. Then there's the question of resource allocation. Who decides how the limited supplies are distributed? What if medical supplies run low and someone needs treatment? Do you save the mission-critical engineer or the scientist whose research is less essential to survival? These are trolley problem ethics questions that stop being philosophical exercises when they become real decisions with real lives at stake. And reproduction. Let's address this directly because it's going to come up. If the crew is on Mars long-term or permanently, human biology is going to assert itself. People will form romantic relationships. The question of whether to allow or forbid reproduction becomes urgent. On one hand, a pregnancy on Mars would be incredibly risky. We have no idea if human gestation can occur normally in low gravity. The radiation exposure alone might cause severe fetal abnormalities. The medical resources required for childbirth might exceed what's available. On the other hand, if you're establishing a permanent settlement, eventually reproduction becomes necessary. You can't maintain a population solely through immigration from Earth. The costs are too high and the logistics too difficult. At some point, for humanity to truly become a multi-planetary species, children must be born on Mars, but those first children would be subjects in an uncontrolled experiment. We'd be discovering in real time what low gravity and high radiation do to developing humans. The ethical implications are staggering, yet the alternative might be accepting that Mars can only ever be a temporary way station, always dependent on Earth for new personnel, never truly independent. This brings us to an uncomfortable truth about the entire Mars colonization project. It might require accepting risks and making ethical compromises that would be completely unacceptable on Earth. We might have to accept higher mortality rates. We might have to allow experiments on human development that would never pass any ethics review board. We might have to acknowledge that some people will die, possibly in horrible ways, and that's just the cost of expanding humanity's presence beyond one planet. Is it worth it? That's a question every generation will have to answer for themselves. Some people argue that becoming multiplanetary is essential for humanity's long-term survival. If a catastrophic event wipes out life on Earth, an asteroid impact, a nuclear war, a pandemic, a runaway climate shift, having humans living on Mars means our species survives. We've backed up humanity, created a redundancy that makes our extinction less likely. Others argue that the resources, money, and effort required to colonize Mars would be better spent solving problems on Earth. Why struggle to make Mars habitable when we're actively making Earth less habitable through climate change, pollution, and environmental destruction? Shouldn't we fix our own planet before we try to settle another one? Both arguments have merit, and the truth is, it's not an either-or proposition. We can work on solving Earth's problems while also pursuing space exploration. Humanity has always been capable of doing multiple things simultaneously. But the question of priorities, of where we allocate limited resources and attention, remains contentious and important. What's fascinating is how the first Mars crew's experience might shift this debate. If they thrive, if they establish a successful, sustainable presence, if they demonstrate that humans can live on Mars long-term, it will energize the colonization movement. But if they struggle, if the mission fails, if people die in preventable ways because we underestimated the challenges, it could set back Mars exploration for decades. The first crew carries the weight of humanity's multiplanetary dreams on their shoulders. They're not just explorers, they're proof of concept. They're demonstrating whether this entire endeavor is feasible or folly. There's something we need to confront directly, the very real possibility that the first Mars mission ends in tragedy. Not because of poor planning or incompetence, but simply because the universe is indifferent to human ambition and Mars is a profoundly dangerous place. History is littered with exploration disasters, moments when bravery and preparation weren't enough to overcome the raw hostility of the environment. The Challenger explosion in 1986 killed 7 astronauts just 73 seconds after launch because of a failed O-ring seal. The Columbia disaster in 2003 killed 7 more when damaged heat shield tiles allowed superheated gas to penetrate the wing during re-entry. The Apollo 1 fire in 1967 killed 3 astronauts during a ground test because of a spark in a pure oxygen atmosphere. And those were missions close to home, where we understood the environment, where we had decades of experience, where rescue was theoretically possible. Mars is none of those things. It's a frontier where our experience is minimal, our understanding incomplete, and rescue impossible. When something goes catastrophically wrong on Mars, people will die, and there's nothing anyone can do to stop it. The folks back on Earth will receive the telemetry, the final transmissions, hours after everyone is already dead. They'll analyze what went wrong, learn from the disaster, and hopefully prevent it from happening again. But that knowledge will be purchased with lives, with families who lose parents and spouses and children to the void. This is the bargain we make with exploration. Progress often requires sacrifice. The question is whether we're prepared to accept that sacrifice when it comes. When the first grainy images of a Martian dust storm destroying a habitat reach Earth, when we hear the final messages from a crew slowly suffocating as their life support fails, will we have the stomach to send another mission? Or will we collectively decide that the price is too high, that some frontiers should remain uncrossed? I don't know the answer. But I know that the first crew on Mars understands this possibility intimately. They've signed up knowing that they might not come back, not just because of mission constraints or economics, but because they might die there, and they've made peace with that, which is either incredibly brave or slightly insane, and perhaps those two things aren't so different. Let's talk about something more hopeful, though. Let's imagine that the mission succeeds. The crew lands safely, establishes their habitat, begins their research, and manages to survive. What would they actually discover? What makes Mars scientifically valuable enough to justify all this risk and expense? Mars is our best opportunity to answer one of humanity's most profound questions. Are we alone? The search for life, past or present, on Mars is a primary driver of exploration. We know that Mars was once very different than it is today. Billions of years ago, Mars had a thicker atmosphere, liquid water flowing on its surface, and conditions that might have been suitable for life to emerge. Evidence from rovers like Curiosity and Perseverance, which have been exploring Mars since 2012 and 2021 respectively, has found ancient riverbeds, lake deposits, and minerals that form only in the presence of water. The Perseverance rover has been collecting samples from Jezero Crater, a location that was once a lake fed by rivers. These samples might contain fossilized microorganisms or chemical signatures of past life. But here's the challenge: those samples need to come back to Earth for detailed analysis, or we need to send sophisticated laboratories to Mars. A human crew could conduct this analysis directly. They could make intuitive decisions about where to drill, which rocks to analyze, and how to interpret unexpected results in ways that remote robots, even sophisticated ones, simply cannot match. If we found definitive evidence of past life on Mars, even just fossilized bacteria, it would be one of the most important scientific discoveries in human history. It would tell us that life isn't unique to Earth, that wherever conditions are suitable, life finds a way. It would revolutionize our understanding of biology, evolution, and our place in the universe. And if we found evidence that life emerged on Mars independently from Earth, that would be even more profound, because it would suggest that the universe is teeming with life, that we're not special or unique, just one example among countless others. There's also the possibility, remote but tantalizing, that microbial life still exists on Mars today. Perhaps in underground aquifers protected from the surface radiation, perhaps in seasonal flows of briny water that appear during Martian summers. If living organisms exist on Mars right now, studying them could reveal alternative biochemistries, different solutions to the problems of life that evolution on Earth never explored. But here's where things get ethically complicated. What if we contaminate Mars with Earth life? Every spacecraft we send, every rover, every piece of equipment gets sterilized before launch to prevent biological contamination. But sterilization isn't perfect. Bacteria are incredibly resilient. Some can survive radiation, extreme temperatures, even the vacuum of space. There's a real possibility that we've already introduced Earth microbes to Mars, and we just don't know it yet. When humans arrive, the contamination risk increases exponentially. We're walking biomes carrying trillions of bacteria in and on our bodies. Our habitats will contain Earth microorganisms no matter how careful we are. If any of those organisms escape into the Martian environment and somehow survive, we've irreversibly changed another planet's biosphere. If Mars is sterile, maybe that's acceptable. But if Mars has its own native life, even just microscopic organisms, introducing Earth life could be catastrophic. Earth bacteria might outcompete Martian organisms, driving them to extinction before we even discover them. We could destroy the very thing we traveled all that way to find, committing an act of unintentional genocide against the only other life we've ever encountered. This is why planetary protection protocols are so strict and why some scientists argue that humans shouldn't go to Mars at all, at least not until we've thoroughly searched for native life using robotic missions. But others counter that humans will eventually go regardless, so we should do it thoughtfully and carefully rather than wait until commercial interests make it happen without proper oversight. The debate continues, but I suspect the human imperative to explore will ultimately win over the cautious scientific approach. We're a species that climbs mountains because they're there, that sails across oceans to see what's on the other side. Mars is the next horizon, and we're going to cross it, whether it's wise or not. Beyond the search for life, Mars offers insights into planetary formation and evolution. By studying Mars geology, its atmosphere, its magnetic field history, we learn about how rocky planets develop and change over billions of years. Mars is like a fossil of what early Earth might have been like, frozen in time because it's smaller and cooled down faster than our planet did. Understanding why Mars lost its magnetic field, why its atmosphere thinned, why the surface water disappeared, these questions have direct relevance to Earth's future. Could Earth lose its magnetic field? Could our atmosphere thin? What conditions are necessary to maintain a habitable planet over geological time scales? Mars is our laboratory for planetary science, a place where we can study processes that are difficult or impossible to observe on Earth. There's also resource potential. Mars has water ice, carbon dioxide, minerals, and potentially useful ores. While we're not going to ship Martian resources back to Earth because the transportation costs would be absurd, those resources could support a Martian settlement and eventually fuel deeper exploration of the solar system. Water can be split into hydrogen and oxygen for rocket fuel. Metals can be refined for construction. The regolith itself can be used for radiation shielding or processed into building materials. A self-sufficient Mars base could become a staging point for missions to the asteroid belt, where truly valuable resources exist in abundance. Some asteroids are essentially solid metal, containing more platinum group elements than have ever been mined on Earth. If we establish mining operations in the asteroid belt, Mars could serve as a way station, a place to refuel and resupply before returning to Earth or heading deeper into space. This vision of Mars as a stepping stone to the wider solar system is appealing, and might ultimately justify the enormous investment. But it's a long-term vision, spanning decades or centuries. The first crew on Mars won't see it realized. They'll be focused on survival, on establishing the basic infrastructure that might, someday, enable that grander vision. And that's another reason they might never return. If you're the foundation upon which future expansion is built, leaving means abandoning that foundation. The first crew's presence, their continued work, their accumulated knowledge of living on Mars, all of that becomes too valuable to lose. They become, in a sense, prisoners of their own success. The better they do at establishing a foothold, the less likely it becomes that they'll be allowed to leave. Mission Control might start phrasing it gently. We'd like you to stay another year to train the next crew. Then it's, the funding for the return mission has been delayed. Then it's, honestly, you're more valuable there than you would be back here. Eventually, nobody says anything at all. The return mission just never materializes, and everyone quietly accepts that this was always how it was going to end. There's a particular kind of betrayal in that scenario, isn't there? The astronauts who signed up were promised a return. They accepted the risks of the journey, the hardships of Mars, the years away from home, all with the understanding that it was temporary, that they would come back as heroes, reunite with loved ones, share their experiences, and live out the rest of their lives on Earth with the knowledge that they'd done something extraordinary. But if the return mission never comes, if the promises evaporate into budget cuts and shifting priorities, those astronauts become exiles. They didn't volunteer for a one-way trip. That choice was made for them by bureaucrats and accountants sitting in comfortable offices on Earth, people who will never experience the consequences of their decisions. This is already happening in a way with the International Space Station. Astronauts occasionally have their missions extended beyond the original plan because of scheduling issues, transportation problems, or other logistics. They signed up for 6 months and end up staying 9 or 12. It's frustrating and difficult, but it's still measured in months, not years, and Earth is always visible below them. On Mars, an extended mission might mean years, even decades. It might mean never. The psychological impact of this betrayal would be devastating. Imagine the moment when you realize, truly understand that you're never going home, that the people who sent you here have abandoned you, that all the sacrifices you made were based on a promise that won't be kept. Some people might handle it with stoic resignation, others might become bitter, angry, depressed, a few might break completely. And here's the worst part. The people on Earth will move on. The news cycle will shift to other stories. The initial excitement of the Mars landing will fade. People will stop paying attention. Your regular video updates, your messages from another world, will become routine, unremarkable, something that gets posted to social media and ignored. You'll be forgotten while you're still alive, marooned on a planet that most people think about as often as they think about the composition of asphalt. This is the fate of pioneers throughout history. The first settlers in any new land faced incredible hardships, struggled to survive, often died without seeing the fruits of their labor. Later generations reaped the benefits built on that foundation and maybe occasionally acknowledge the sacrifices of those who came first. But in the moment when you're the one struggling, when you're the one abandoned, historical significance is cold comfort. Let me tell you about something that makes this even more complex: the legal status of Mars. Who owns Mars? Who has jurisdiction over crimes committed there? Who can exploit resources? The Outer Space Treaty of 1967, which has been signed by most spacefaring nations, states that celestial bodies cannot be claimed by any nation. Space is the province of all mankind, and nations can't exercise sovereignty over the Moon, Mars, or other bodies in the solar system. But the treaty is vague about individuals and corporations. If a private company like SpaceX sends people to Mars and establishes a base, do they own it? Can they claim resource rights? Can they establish rules and governance structures? The treaty says Nations can't claim territory, but it doesn't clearly address private entities. And what about crimes? If someone commits murder on Mars, what legal system applies? The Antarctic Treaty provides some precedent. Crimes in Antarctica are prosecuted by the perpetrator's home country. But Antarctica is still on Earth, relatively accessible with established protocols. Mars is different. Extraditing someone from Mars for trial on Earth is logistically absurd. You can't just send them back. They might be physically incapable of surviving Earth's gravity after years on Mars. So does the Mars settlement establish its own legal system? Do they conduct trials and impose punishments? Who gives them that authority? What if their system violates the laws or values of the nations that sent them? You can see how quickly this becomes complicated. There's also the question of citizenship. You're born on Mars. What country are you a citizen of? Your parents' nationality? The nation that funded the mission? Or are you something new entirely, a Martian citizen of an as-yet undefined political entity? And what rights do you have? Can Earth nations impose laws on you when you've never set foot on Earth? These aren't just theoretical questions. They'll become urgent, practical issues the moment permanent settlement begins. And the lack of clear answers creates a legal and political grey zone that could lead to conflicts, exploitation, and injustice. Imagine this scenario. A corporation funds a Mars mission with the promise of profit from resource extraction. The crew members are employees, not government astronauts. They're working under contracts that might include provisions giving the corporation control over their lives, their time, their output. If conditions become intolerable, if the corporation is exploiting them, violating their rights, treating them as indentured servants, what recourse do they have? They can't quit and go home. They can't strike effectively. They're completely dependent on the corporation for their survival. This is colonialism replaying on another planet. The same patterns of exploitation, coercion, and abuse that characterized Earth's colonial history could emerge on Mars, and we might not even recognize it happening until it's too late to stop. Some people argue that we need a comprehensive legal framework for space settlement before we send permanent crews to Mars. Treaties that protect workers' rights, establish clear governance structures, prevent exploitation, and ensure that Mars development benefits all of humanity, not just wealthy corporations or nations. Others argue that trying to impose Earth-based legal frameworks on Mars is impractical, and that Martian settlements should be allowed to develop their own systems organically. Both positions have merit, and the tension between them will shape how Mars colonization unfolds. But I suspect the reality will be messy, improvised, and frequently unjust, just like most of human history. We'll make mistakes, learn from them slowly and painfully, and hopefully eventually develop systems that work. But the people living through that transitional period, including that first crew, will bear the costs of our collective learning process. Now let's talk about something that might sound science fiction but is actually a serious concern. What happens if the Mars crew decides they don't want to follow Earth's directions anymore? What if they declare independence? It sounds absurd until you think about the practical realities. Mars is 8 months away at best. Communication has a delay of several minutes to over 20 minutes each way, depending on orbital positions. Earth can send instructions, but it can't enforce them. If the Mars crew decides to ignore orders, what's Earth going to do? Send a military force? By the time they arrive, more than a year and a half will have passed, and when they get there, they're just as vulnerable and dependent on the infrastructure the original crew controls as anyone else. The Mars crew has something extraordinarily valuable. They're there, and everyone else isn't. They control the habitat, the life support, the equipment, the knowledge of how to survive on Mars. That gives them leverage. If they decide that the terms of their arrangement with Earth need to change, they're in a surprisingly strong negotiating position despite being completely dependent on Earth for supplies. Of course, Earth controls the supply line. No more shipments of spare parts, electronics, medical supplies, or luxuries would be a powerful counterlever. But if the Mars crew has achieved even partial self-sufficiency, if they can survive without regular resupply, suddenly the balance shifts. They might be uncomfortable without Earth's support, but they won't die, and that changes everything. This is speculative, but it's based on historical precedent. Colonies throughout history have eventually sought independence from their founding nations, often successfully. Distance and communication delays make central control difficult. Local interests diverge from distant authorities. People who are living with the reality of a situation make different decisions than people managing it from afar. The first Mars crew probably won't declare independence. They're too dependent, too small, too vulnerable. But the second crew, the fifth, the 100th, at some point, if Mars settlement continues, there will be people who've lived their entire lives on Mars, who have no personal connection to Earth, who see themselves as Martian rather than American or Chinese or European. When that generation comes of age, they're going to ask hard questions about why they should follow orders from a planet they've never seen. And honestly, it's hard to argue with them. Self-determination is a fundamental principle we claim to value. If Martian settlers want to govern themselves to make their own decisions about their lives and their world, on what basis do we on Earth claim the right to deny them that? Because we paid for the initial missions? Because their ancestors came from Earth? Those arguments sound uncomfortably like justifications for colonialism, and we've supposedly learned that lesson. So Mars might become independent, not through revolution or conflict, but simply through the practical realities of distance and time. Earth's control will gradually weaken as Mars becomes more self-sufficient, until one day everyone simply acknowledges what has already become true. Mars is its own world, with its own people, its own interests, and its own destiny. But that's the long view spanning generations. For the first crew, independence isn't an option. They're pioneers, not colonists. They're establishing a foothold, not founding a nation. Their concerns are immediate and survival-focused. Keep the habitat functioning, don't die. Complete the mission objectives. Maybe, just maybe, live long enough to see home again. Except home is becoming an increasingly ambiguous concept. After years on Mars, is Earth still home? Or has home become a cramped habitat module on a frozen desert planet where every breath is manufactured and every drop of water is recycled from your own waste? When your entire world shrinks to the confines of a base and the immediate surroundings you can reach in a spacesuit, when you spend more time thinking about methane production rates than about forests and oceans, when you measure time by the Martian sol instead of the Earth day, something fundamental shifts in your identity. If you are still watching, I am sure you will love this other video. At the left side of the screen, how long would it really take to reach Pluto and Alpha Centauri? Discover why interstellar travel requires multi-generational thinking and how weight equation paradoxes challenge mission planning. See you there.